Right now there is nothing here, so I'm going to do that. Layout tab is done. Then if you look into that tab, selection is done, copy. That's where I'm saying that I will copy the other floors from typical floor. Okay, so that's one thing. Another one is import from DXF file. That's where we usually, when the architect sends us a CAD file, and we take the CAD file and convert it into a DXF file, and then import that DXF file in RAM. That means we already get all the information that the architect wants us to know, like the location of our columns, location of all the grids, okay, location of our walls. Okay, so if the architect wants us to use there, we can use it. Okay, so that's an very, I mean, most of us do that. Right now, we will go to the next item, which is grids, and I will create a grid, and I'm going to give a name. Orthogonal. Orthogonal means like perpendicular. And I'm going to add, and then select, and then edit grids, which is basically what we are going to do, like 1, 2, 3, A, B, C, D. So first grid in the X grid means the ones that are vertical, okay? And the first grid is 1, grid coordinate is geometry, coordinate is 0, and I'm going to add it. Now if you look into that, I have like 2, 3, 4, 5, they're all equally spaced, right? So if they're equally spaced, I can generate one and then I can place it. So I can use the grid spacing as 30 feet, and number of additional grids, probably I will add another 4 of them, and I'm going to say add. That means you can see they automatically generated the other grids. Same thing I'm going to do for Y grid, and the first one is A, and the coordinate is 0, 0, and spacing is 25 feet, and I'm going to say additional 4 grids. So A, B, C, D, E. Yes.
Can you add 2 different types of geometries on the same grid? Like you do this and then you add a radial next to it?
Yeah. So we are done with the geometries, so I'm going to say add. You can always add another.
And you'll go to the same plane with the same origin?
Yeah.
Okay.
Yeah, same radial. It's just a grid. Plane you are defining as typical. That's your plane.
Yeah.
So we are done with the grids, so we'll just click on that, okay. And since there is nothing, I need to see the grids, so click on this, select grid system. And for a typical floor, I'm going to select the orthogonal, and now it shows all the grids.
Wow.
Hmm?
Wow.
You are impressed with this one already? No, you'll be impressed. Okay. So we have the grids, okay? Now, what is next? Tab is gone, grid is gone, then we have to create columns, okay? Usually if you look into that, the columns are added on the intersection of the grids, okay? So I need to kind of like add on grids, click on that. Now, if I add on grids, there will be columns like that. Usually, I'm going to use a wide flange section. I do not know the size yet, but we will learn it, okay, or we will design it. At the beginning, I will say that let's start with gravity framing, okay? At the level of moment frames and brace frames, those will be lateral, okay? But we can always change the property. Geometry is I section. You can use tube, rectangular HSS or round HSS if you want. But I like this one because that's more commercial one. So single, if you click on that single, it will click on the single intersections. But if you know that you will have columns everywhere, you can do right click and do a fence, click and fence it.
So
You will be impressed the whole day today.
the columns
Which is good.
For in reality they change from like side to side and stuff like that, right?
Orientation?
orientation, yeah.
Yeah, we will do that. No, I'm happy that at least I get somebody who's excited. Okay. Yeah, excited means fine, but you have to show how you are doing it. Okay, that's the excitement I get. Okay, so we are showing the columns, but not done properly. Okay, we will have to change some of them. Now, after the column, we will get the beams, and if you see the major ones, the garter ones are connected between columns and columns. Okay, so we'll connect them first. So add-on grids, and again, I will say that my first beams are gravity beams, composite. Okay, that's a default. Composite is basically, you will learn it, not probably, the last topic of our course, which is a composite beam section. And actually that is not part of our syllabus, I'm just adding that because you need to know, because it's been done, or it's always been there. Composite sections are like when you have a deck on the top of the beam, and the deck carries concrete, and if there is a bending, positive bending on the beam, that means top part is in compression and the bottom part is in tension. And if it is top part is in compression and the top part of the beam has a deck which carries concrete, and the advantage for concrete is that it can take a lot of compression. Okay, so if we are providing concrete on top of the steel beam and it is in compression, why don't we take the advantage of concrete being there, take the compression? You follow me? And if that is the case, then lot of the steel does not need to take the compression anymore. That means the steel beam is solely for taking tension. Okay, so normally half of the beam takes compression and half of the beam takes tension. If the whole beam takes tension and the concrete takes compression, then I need reduced size beams to take the whole the moment. Okay, you follow me? So that's why we want to use composite action. The only thing is the beam has to be in positive bending. That means it has to be positive. That means compression should be in the top. If it has a negative bending, tension in the top, concrete cannot take any tension, so it will not work. Okay, so composite action only works for positive bending. Where is the positive bending? When there is a gravity load and the beams are simply supported. That's when you have positive bending. Okay? If you have a negative bending, say for example moment frames or brace frames, you'll have a negative bending because it goes laterally. So your bending moment diagram, half is in positive, half is in negative. That's not going to work.
Unless you like separate the concrete, right?
What do you mean by that?
So let's say you pour the concrete and then you separate at the point of where the moment changes, then you have two positive moments for the concrete.
I don't understand what you're talking.
So the reason you have a negative moment is because there's another support in the middle, right?
No,
Then how can you get a negative moment if it's still supporting on both sides?
if you have a fixed connection. If you have a fixed connection, it is a negative moment. Okay, so I'm going to add beams like that. Now again, it is time consuming. If I know, I can go a fence and I can do that.
Excuse me, time to bring that.
Right click. Oh, you didn't say wow.
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 Okay, now you'll say wow. Okay, now I have, if you see, I have to give intermediate beams at 10 feet intervals. So I can say go layout, beams, add off grid, and I say parallel to beam and 10 feet. Okay, and say click. Like that. Again, it's time consuming. So if you go layout, beams, add generation, and I'm going to say number of equal spaces per beam 3, add, and if I say, it will automatically generate. So equal spaces, 3 spaces, okay? So you do not have to calculate 10, 10, 10 or 9, 9, 9 or whatever it comes up. Same thing here. Okay. Okay. So my beams are done actually. The next step is I know that I have moment frames and brace frames, right? So I have moment frames these 3, this one, and I have moment frames here, and I have brace frames these 2, right? Okay, so let's do that. Now, since moment frames or brace frames, what are those? Moment frames is basically beams and columns. Only thing difference is their connection, and they are supposed to take lateral loads instead of gravity loads. So all of these in the middle are all, I'm saying that these are gravity loads, and the connection between this beam and this beam and that beam is all simple connections, okay, bolted connections. That makes my life easy. That means these beams will be all positive bending moment, and they will be composite beams. So let's change these frames to frames, okay? That means I need to convert that column to take lateral loads, that beam to take lateral loads. How I do that? I can use layouts, columns, and then change properties, okay? Now if you see columns, this one, and if you click on this one, they're basically same thing, okay? These are all listed here, okay? So either you can go layout, columns, or you can click on that and you can change. So I'm going to use this one, change column, and change the framing first, okay? Framing from gravity to lateral, okay? Are you with me?
Yes.
Okay. Another thing is, if I'm saying that framing is in this direction, look at the column orientation. It is connected with the weak axis, right? I want to get the maximum possible stiffness in that direction. So I'm going to change the direction, which is orientation, and I'm going to make it like that. You follow me? That answers your question, okay? And I'm going to use a fence to convert them. If you see, now it's red means it's lateral and the orientation is changed. Same thing I'm going to do here. What about these ones? These are lateral, but the orientation should be same, right? So I'm going to right click and just change, the framing is already lateral. I'm going to change it to this orientation and say that like that, okay? Now the columns are done. I need the beams to be done. So I'm going to go layout, beams, change properties, and the framing should be lateral, and composite flat. Do I need composite flat? No, we expect that it will have negative moment, so don't worry about composite flats anymore. Okay, it will be non-composite. Even though if it is shown as composite, it will be non-composite. You don't have to worry. Another thing is, what about the orientation for the beams? Beams are always oriented in one way. Beams are not flat. Beams are always vertical. So beams are always rotation about their strong axis. So right now all of them are showing as moment frames. For the brace frames, we have to do it in an elevation view once we have the story options, okay? So we'll pause it for a while for the, leave it for a while for the brace frames. Are you following me? All of you? Okay. So we'll come back to the brace frames when, or defining braces when we are in a position to give, we have the story of, story defined. Okay. Now, what is next? Slab. right now these are all showing as the center line of the beam, so my slab cannot stop here. Okay, my slab has to go over the half center line and then go at the end of, at least to at the end of the beam, at least at the end of the column. Okay, so we need to kind of like have an overhang from the center line of the beam. Usually I give 12 inch if there is no shade or anything, no extra. If the architect wants 2 feet, he can give it to us and we can actually model it. So I'm going to give a slab edge and I'm going to say it's a 12 inch overhang. Now, overhang in this direction or outside? It must be outside, not inside. Okay? So I'm going to use an overhang, and left and right means if you try to give one by one, then you follow your path and find out whether it needs left or right to give you an overhang. Right now I'm going to say that whole perimeter, so it's drawn a slab edge on the whole perimeter. Okay? Are you with me? Now, next thing is I need to give slab deck assignment. I need to assign some deck. Okay? Right now there is no decks are assigned, so I need to assign the decks. So to do that, I need to go to the prop table. Prop table and decking means I need to use a deck. Now the decking that I use commercially is Verco W3. I'm just giving a name. Concrete thickness above fluid is 3.5 inch. Start length 5.5 inch. Unit weight, right now it's lightweight concrete. I want to use regular weight. F prime is 4 KSI. Effective thickness is 3.25. Poisson's ratio is 0.3. So these numbers, take a picture of that, you will be using that. Okay. Now, do you follow what I'm doing here? What is the deck size? Okay. So if I'm going back, what is someone choose? I'm going to show you what is the actual deck I'm using. I don't need to look at them. I'm using this one, Verco W3 normal weight concrete 6.5 inch. The deck looks like that. If you look into that, this is the deck. It's a kind of like a white flange W shaped or W3. And what W3 means, this length from the top of this one to the bottom is 3 inch. Okay, and it looks like almost like a W. So if you look into that, there is a groove here and comes back like that. Weight of the concrete is 60 psf. Remember in our exams we gave like 75 psf or 80 psf. That's where I got that load. Okay, and which means I have another 3.5 inch concrete on top of that fluid. Okay, so total is 3 inch plus 3.5 inch is 6.5 inch. That's the depth of the concrete. On top of the fluid is 3.5 inch. Are you with me?
Yes.
So, if you see, I'm saying that concrete thickness above fluid is about 3.5 inch. Stud length. Stud length means, what are those studs? Studs are okay. Studs are basically these ones. Okay, what is that? It's kind of like a bolt welded to the bottom of the stud, and the deck as well as the top of the flange are all welded together. Okay, so it's a one single. And if you look into that, where are my studs? So why we need them? We need them because the concrete can start moving on top of the steel deck. So we need to prevent the concrete to move out or concrete movement. That's why we provide studs. This acts as a shear key. It prevents the movement of the concrete as in shear. I'll show you physical studs. Okay. So if you look into that, that's how the studs are laid out. Okay. Now they are not laid out that spacing wise, they are much more closely, about 12 inch on centers. There are some pictures of the stud. Anyway, okay. So that's another 5.5 inch. Okay. I have total 6.5 inch. Out of that, stud has to come out. Now stud has to come out above the fluid. Okay. So that's 3 inch. The rest is same. Effective thickness is 3.25, not 3.3, and 3605 is the concrete's modulus of elasticity. If you are using 57,000 root F prime C, it will come out like that. Okay, and I'm going to say add, and I'm going to say okay. Now my property of the deck is defined. I will go back and slab, and I'll say deck assignment, and I'm going to say that this is the deck, whole diaphragm, find out. Okay, so I already defined the deck assignment. Now, say for example, I want an elevator core. Okay, I want an elevator core in this zone. Okay, so what I need to do, I need to kind of like open the slab. I did not show it in concrete, but listen to that. So go to slab opening, and I'm going to say that overhang 12 on the left, and if I'm saying that I have an opening, the opening should be inside overhang, not outside. Okay. Already opened up. See? So the program knows where to open up. Now remember, I opened up any opening that you may have in a slab system. Doesn't matter whether it's a timber or plywood, shear wall, plywood roof or floor, or if it is a steel, or if it is a concrete. It has to be bounded by beams. That means we need to stitch it. Otherwise, there is a possibility of crack generation and crack propagation. So it's always, you have to provide a boundary for an opening. Okay, I'm just leaving with that. Now what is next? Loads. That means I have to find out loading. Okay, so the loading is not there, so I have to go back property table and define some loads. First thing that I will do is the surface loading, PSF loading. And I'm going to say that dead load is what? 75 PSF. Okay. Remember, I showed you 60 PSF for the deck load, plus another 15, right? Additional floor finish and so on. So 15 PSF. Construction dead load. What is construction dead load? Construction dead load is the load when we pour the concrete on top of the deck. Okay? So what is the problem? When we pour the concrete on top of the deck, concrete is what? Wet concrete, right? It does not have any strength. So it only, what it does is it gives the weight to the deck, and it takes the load and put it in the beam. That means those beams have to be designed as a regular non-composite beam. You follow me what I'm saying? Okay. Earlier we defined that, okay, all the beams should be designed as a composite beam. Yes, but when? After the concrete is hardened. Okay. But before the concrete is hardened, the beam has to take the weight of the concrete. Okay. So beam has to be designed based on. So what is the difference? Well, the difference is the beams are only taking the dead load of the concrete. It is not taking any live load or the floor finish. It's just taking the weight of the concrete. That's why I am giving a 60.4 PSF as the dead load of the concrete. Okay? There is no additional floor finish. There is no live load added. Now, that's why if you have seen that I showed you, usually when we design steel structure, we don't design steel decks to take loads with shoring. Okay? Because the shoring of the decks are costly. The decks are stiff enough. It's a steel deck, so they are stiff enough to take the loads by itself. And that is why we don't span them more than 10 feet. Because if it is more than 10 feet or 20 feet, 30 feet, the deck will collapse without shoring. Okay? So we are reducing the shoring cost, but at the same time we are adding beams in the middle also. Okay? So I'm going to use that live load 50 PSF or 40 PSF? 40 PSF live load, reducible, yes. If it is at the roof level, you can click on that. If it is like more than 100 PSF, so it's a storage, don't use that. Okay, use storage, that means it cannot be reduced. If it is, you do not know, but it's more than 100 PSF, it's unreducible. Okay. So we are going to say add, and we are done. Huh?
About construction live load.
Oh, I didn't give it?
No.
Oh, okay, sorry. Why did I miss that? Sorry, I did. What happened? Oh, this one. I need to change, so partition, I should have 10 PSF, but I forgot that. Construction live load. During the construction, people will walk on top of that, so your beam has to take that. And usually that's about 25 pounds per square feet. Mass dead load. Mass dead load is for seismic force, because the seismic force acts at the center of mass with the mass, right? So I need mass dead load is the 75 PSF at least. Sometimes we add half of the partition load, another 5 PSF, maybe 80 PSF. If you think that your mass could be a little bit more, feel free to add that. Okay. Now don't add like another 200 PSF. It's like maybe another 10, 15 will be fine. Not more than that. And then I need to change it. Okay. Yes. Question? Now we also want to give a line load. Line load means it's the wall load. Now usually a building will have a perimeter wall, that's fixed. Internally they have partition walls, that's not fixed. So I'm going to use a perimeter wall. Dead load is 0.18. I'm saying that wall on 1 square feet of the surface area of the wall is about 15 pounds per square feet. 12 feet high wall, so it's about 180 pounds, means 0.18 kip per feet. Okay, so I am going to use that. Walls doesn't have construction dead load, walls don't have live load, walls don't have partition loads, not that. If you want, you can add wall load as your mass dead load. So you can say 0.18 kip per feet, and you are going to add that.
This is not reducible, right?
Zero live loads.
There is no live load.
Oh.
Now, why we need that wall? Also, if it is a glass wall, remember that on glass walls cannot deflect a lot. That means the beams below the glass needs to be designed for very small deflection. The amount of deflection allowed is 0.5 inch. Okay, so that's why you need to know where is your wall and how much load it is going to give it to the beam. So the beam cannot deflect more than 0.5 inch. Okay, I'm going to say okay. Now let's apply the loads, surface load, and I'm going to say this is the floor load applied everywhere in the diaphragm. Live load, this perimeter wall load is applied at the whole perimeter. So that's my perimeter wall loads. Okay, I am more or less done with the design or with the modeling of the typical floor. And as I said, I will convert or copy them for the first floor as well as on the roof. So how do I go? Go here, first floor doesn't have anything. So go layout, type, copy, and copy everything from the typical floor. Done? Okay. Also go to the roof level and layout, type, copy everything from the typical floor. Okay, done. Okay. Now roof live load, you may want to change it. If you want, you can change it. Let's see. Let's say roof live load, and we are going to use roof. Usually have less amount, but we are going to say that 20 PSF. The dead load remains same. Roof doesn't have. Roof should not have any partition load. It's a roof, and I'm going to add that. I'm going to say layout, loads, line load. One second. Layout, loads, surface load, and I'm going to say okay on top of that. Now that's the roof live load now. And also I have on the first floor I don't need to change the loading, but only thing that I need to add is the foundations, which is our next step. Foundations will have individual column foundations and also moment frames and brace frames. I need moment frames and brace frames to be continuous foundations. So layout, foundations, individual column footing, add, and I think I will not change anything. Fans. Okay. These are my columns which needs individual column foundation, and I will need individual continuous foundation. Okay, so foundations are done. What else I need? Frame numbers. I'll do that. Now my typical floor, first floor and roofs are done. So I need to give story information. So story information means first floor, and splicing means do you want to change the column sections at that level? No, I want to change the column sections at third floor level. And the floor to height is that.
You only want the roof.
Sorry, what did I do?
Change the number of levels.
No, he adds it and it changes.
Sorry, I was wrong. First floor, no, add it. Then second becomes typical, add. Third becomes typical, but I want the splicing. Fourth, typical, no splicing, add. Fifth, typical no splicing at, and sixth, I'm going to say it's the roof.
Professor, do you not need a splicing for the roof?
No, that's the end of the story. That's the end of the column.
Okay.
You don't need splicing. Okay? Now, I want to see whether it's working. Yeah,
Wow.
this is my building, the frame of the building. Okay? Okay? Now, remember I mentioned that I will give brace frames on the elevation. Now I have an elevation. Before that I did not have any elevation because that was only one story. So I'm going to go click on that and click on that. And I'm going to give some braces and layout braces at standard. I'll use chevron. Okay. FY should be 46 KSI because I'm going to use HSS rectangle. And I'm going to use a fence to give me the braces. Okay. Also, for this program, you need to give the brace sizes also. Okay. The other parts you don't need to give any size, but for the braces you need to give sizes. And I'm going to use rectangular HSS. Say for example, I'm going to use 12 W HSS 12 by 8 by 5/8. That size. And if I click on that, that will show me all the sizes here. Okay. Same thing, I need to do braces here. And I'm going to use the chevron. And I need to give the brace sizes. Okay, I'm done.
How'd you get to the
Now you
The other
can see the
side.
braces.
so you were on one side and you went to the other side?
He just clicked it.
He looked it on the other side.
He just clicked on the other side.
I'll show you. So, if we done, so
Oh,
go
okay.
to the
I got you.
elevation.
Yeah, I understand.
And click on that, you will get that. Okay, so far our model is done. I want to check whether my integrity is fine, so I will check with the integrator, which is means gravity and framing. 120 warnings. Don't worry about warnings. Okay? As long as it's not a error. Okay. Don't worry about the warnings now. You'll see that all the frame column sizes are not given. Okay. So it expects you to give the frame sizes like moment frame or brace frame sizes. I'm not going to do that because I want to do that later. Okay. If I do that now, it will change. It will be changed. Okay. So I'm not worried as long as there is no error. Okay. Error will be always with the red mark. So don't worry now. By the time, that's okay. I'm fine. And we are done with the modeling part. So I'm going to now into design phases. And that's the beauty part of it. Okay. The beauty part of design is that I'm going to click on the beam designs first, then the column designs. Right? Beam designs. Say I'm going to use a typical. Before we design, we say what is the design code, and I'm going to use the LRFD. Now, unfortunately, my version for this RAM is 2015, so I don't have the 15th code. You will have it 360-15, and I prefer LRFD, so I'm using LRFD code. Okay, it will not be changed that much, but you have, if you download it today or now, you'll have that this should be AISC 360-15. Okay. Now, do you know where is that actually the code in that book? The book gives you all the tables of the geometry, right? That's not the code. The code is actually the chapter 16, the spec. That's your code. Okay? When we say AISC 360-10 or 360-15, that's the chapter 16 we're talking about. So I'm going to use those are as my normal. Deflection criteria, I'm going to use that. Yeah, don't worry about that. Camber. Do you know what is a camber?
Mm-hmm.
Camber means when it is a steel beam, right? So it's even for self weight, it's going to deflect. It's very elastic, right? So what we do is if we expect the beam to deflect when the loads are applied, and we will calculate how much deflection it would be, and 80% of that we will say that okay, that's instead of making flat, okay, if it is a flat, then due to the load it will be like that. Okay, so what we do, we tell the fabricator, don't make it flat, make it something like that. So when the load is applied, it becomes straight with the loading. Okay, that being, this is called cambering, and that is how much we will specify how much we want. 1 inch, 1/4 inch, or depending on how much it will be deflection wise. Okay, so here what we are going to say is that 80% of the dead load should be used as camber, and the camber should be 0.25 inch, and the maximum camber is 4 inch. Actually, I don't want 4 inch because 4 inch cambering, you will see that. If the beam deflects 4 inch, you will feel that or see that okay, it's 4 inch down. Don't allow it. Okay, for 30 feet span, we will say 1.5 inch is fine. So I'm going to use a 2 inch, and also I'm going to do the same thing for non-composite beams. Okay. Now I'm going to design it. I'm not saying wow.
Wow.
Software design.
Wow.
That's a lot.
That's it.
Why are we taking an example without designing this then?
So your beam size, if you see W12 by 19, 10 means now 10 starts in the middle, and C equals 1, that means cambering 1 inch.
Yeah,
Okay?
does it do connection types too?
Mhm.
Oh.
Some, but that has a different model, connection model. I don't have that, but RAM has that. Okay, and if you see the garter beams, 21 by 50, that's the garter size. Okay, so that's your beam, that's your design. Okay, beam design, not the column design. Okay, that's the beam design. And if you want to see what is going on at the roof level, you can see that. Again, the roof level doesn't have any change in loading, so it should be same. What about the floor levels? First floor level. Again, we do not change any loading, so the beam sizes will be same. Okay. Okay, I'm going to. So beam design took only what? Less than 1 minute, 10 seconds actually. Let's go into the column designs first. Now, again, there is a difference between this one and concrete. You were in my concrete class. In concrete, we cannot do that because what? The same column takes moment also. Okay, same beam takes moment because the concrete connections are rigid connections. Okay, even though we are saying those are gravity columns, but that columns takes moments. Okay, here for a steel structure, it's much easier because you are saying that the gravity beams don't take any lateral loadings. In concrete, you cannot just say that because these columns will be taking lateral loadings. Okay, for columns, again, I'm going to use the same code. And as I said, I'm a fan of, not fan, I use LRF dollars. I don't use ASD. Design defaults, that's okay. Trial groups, okay. Trial groups means that I want to use the optimum number between W14, W12 and W10. Which one gives me the optimum design? Okay. Optimum design means I'm going to say that, okay, I want a W14 by 68, whereas a W12 by 50 is sufficient. If that is the case, then the program will choose a W12 by 50, okay, because that's the more cheaper. So I can use W sections, or I can use HSS rectangle, or I can use HSS round. It will give me all the options, okay. So I'm going to say okay. Assigns bracing, it's already done that. Now I'm going to process, design all. Done. Okay?
Oh, and it's used for this demonstration.
Yeah. You will learn that when we are in chapter 5 and 6. What does that mean? It's called interaction scale or interaction diagram. Okay? The value of interaction. Now, if you see, there is no red because it's designed that. There is no red. It's all blue or green. So if we see one of them, it's called view update. Okay, click one of the beam columns. I will see that. Oh, I forgot to show you the beam update in the beam. So when we get out of that, I'll show you. So if I see this column, okay. Now I'm not seeing this one because these are, even though these are lateral columns, right? It's a moment frame. This is a brace frame. These are lateral columns. Right now they are only designed to take gravity loads. Gravity wise they are designed. So they're not designed for lateral. So I'm going to use a normal gravity column. And if you see the optimum numbers, the design is W10 by 49 for the first third floor, and the second top 3 floors is W10 by 33. Remember, I added splicing at the third floor. That means I'm saying that change the section after the third floor. What is the advantage? From 49 to 33. So I'm getting some economy. If I want to use a W14 by size, this would be the size. Okay. Again, it's 14 by 53, whereas 10 by 49 works. If I'm using a W12 by, then 12 by 53, again, options. So these are my options, okay? And the values of interaction is given as 0.69, and 0.69 means 0.69 should be somewhere here. This color, right? Right? Actually it's points. How much was that? Oh, now I'm talking about it. This one. It's 0.83. Right? First floor is 0.83.
Yeah.
And 0.83 is between this one. This one. Okay? Okay, my columns are done. I'm gonna go back to beams once more. Typical. And I wanna show you, say for this one. Okay? W12 by 19, composite beam, how many starts, all this. And you can see view results. That means it will say how much moment it is taking and what are the load combinations it is doing, everything. What is the deflection, how much. Another thing you can see view diagrams. That means what is the moment diagram, what is the shear force diagram.
Trash.
Oh, can you go to the thing, moment frames, and look at the shear diagram?
We're not done yet. Okay, you can do that. Or if you want to see the loading, that's your loading diagram.
Oh, God.
Okay, so we are done with that. Now I want to do the frames quickly. I may need another 5-10 minutes more. Okay. No, you cannot ask me question. No. Okay. So basically what we need to do is give seismic loading and wind force. Okay. So let's go with the seismic loading. Now you have to do very carefully the video or picture because you don't know anything of that. Sorry for that.
Oh.
Seismic. Okay. And I'm going to use an equivalent lateral force method. Unfortunately, or fortunately, usually we should not be using for a 6-story building. Equivalent lateral force method is not applicable anymore because you have to use a dynamic analysis. We are doing a static analysis. Okay. and I'm going to use a and. So I'm going to change a bunch of numbers. X direction we have brace frames, eccentric brace frames, that's actually 7. Sorry, concentric brace frames, special is 7. In the Y direction it's special moment frames, that's 8. These are called response modification factor, R factor. You will learn it in your senior design. Importance factor for this building, office buildings are usually 1.25, that means it's multiplied by 25% more. Soil site class D if you do not have that. SS value is actually given in your, hold on a second, in your handout. SS value is given here. Okay, these are the two values we are going to take, 2.186 and 0.696. What is that? Okay. So it's 2.186, 0.696. Risk category is a 3, and orthogonal conditions. Orthogonal conditions is when we have multiple frames coming in one single column. Okay, 2 frames. We don't have that, so we do not need anything else. Other than that, these are self-calculated, and we are going to do a little bit wind also. Okay, only thing we need to do is say 7.8, and the rest same, remain same. Okay, now we are going to analyze it. Select all. Unstable structure. What is that? That means, what happened? Okay, which means, remember my columns for the frames are designed for gravity load and W10/49 or those, and for seismic load, these are going to fail, and failing in some way that they cannot stand. They are way too much. Remember this thing. I will be saying this thing in our class when we are going on the frame designs. Okay, these are called P delta effects. Okay, that means the deflection is so much that additional moment is generated and it fails. So what we are going to do, we are going to I'm going to erase all, not erase, not showing the gravity system. What we are going to do is we are going to change the column sizes to a huge size, which is W14 by 398. Okay, and I'm going to change the beam sizes also by W18 by 211. It's only for the lateral system, not for that. Now I'm going to go analyze it. It's done. You follow me what I'm doing?
Mm-hmm.
That means my column sizes and beam sizes were so small that it failed.
So can we do it for you? Oh no, this one they can't figure out what it needs to do, right?
Huh?
Does it have an option where it figures out what's the most optimal?
No, that you have to do it by yourself.
Your brain.
That's why we are the engineers, we have that. Now I want to show you a dance. I want to show you that one, okay? So I am going to use one of the X forces, okay? Not 200, maybe 20, and animate. That's how the building will behave under seismic loading in this direction. Okay, the building movement. Okay?
Can you show it from the other view?
Yes, I'm going to. Other view means other direction.
No, I mean like looking at an elevation.
Hold on a second. And what about in the Y direction?
Oh.
What is wrong with that?
Oh.
Same scaling, what is wrong with that? The reason is,
Best friend.
other direction is moment frames. Moment frames is very flexible compared to brace frames.
That's normal. I've seen a building do
No, no. It's not, honestly, it's too much because I'm scaling it to 20 times. This is how the building will behave in real.
Oh, that's
Okay.
scary.
Still a lot,
Yeah, I can imagine.
still a lot.
It's like going to like 20 feet, it's that size.
No, yeah, your movement frames are not enough. Okay, so if I'm going to do that, you want to see from the other side, right? That's how the building will behave.
But it's still stable, right?
No, your movement frame needs to be bigger. It's not sufficient, I would say. Okay, so that's your design, not design yet. Now I want to go quickly, couple of things, analyze. I need to do some load combinations, which is, because remember, 1.2 dead load, 1.6 live load plus seismic load.
Mhm.
It's 1.54. Take this number also. I'm not sure whether you are familiar with the numbers called redundancy. Have you heard the name redundancy? Usually, if you are in the senior design class, most of your teachers will say that use 1.3, okay? Which I don't buy it. Okay? If you, 1.3 means you bump up your loading by 30%. Okay? I need to do quick things, couple of things, which is called some additional checks for California, which is called standard provisions. It's already done. Process member code checks. Look at the columns. I bumped up to what, 14 by 390? Still doesn't work. Okay? Because we have fewer. Why it doesn't work? Let's check it one. Interaction is 3.31. Way too much load. Okay? That means if I were the designer, I would put another frame in the middle. Right now the whole thing stands on that. I'm not going to do anything on that. You know how to do that. You can go and check. Say for example, you can do something like still doesn't work. So basically I have to add another one. Another frame. Another provision is called seismic provision, that you have to do it later. Okay? And that comes from, there is an omega factor, or which is called overstrength factor. That's, again, these are all part of the code. Okay? Now also you have to assign frame type. The first one is concentric special moment frame. And the next one is process, member code check. All of your braces are failing.
Nice.
This is, I'm not worried because my deck is on the other direction. This part is not a problem. Okay, but okay, if you go view update, what is wrong with that? It's, no checks. Okay. So one more. Okay. Yeah?
Can you convert it to Revit
Yes,
too?
right.
Okay.
There we go. One more quick, yeah? So if you look into that, these are all going to give me blue, green. But does that mean that they are designed properly? No. It means that we have done that, but not properly. It's not right. So when you come, a lot of students come to me and say, "Oh, these are all green." No, these are not green. Doesn't mean that you are done. I'm going to use a 36" by 36" plate. Quickly. Geometry.
What is this?
Foundation. Generate for concrete. Just give me 3-4 minutes. Okay, my foundations, the spread footings are done. If you look into that, one of them, it will be 12 feet by 12 feet. Bar size 7, number 7 bar, 13 number 7 bars each direction. So your foundation is done. Okay. What about this one? These are not done yet, so we can click on that. And what does it say? All springs are in tension. So what we need is pump up the size. Okay, so it worked. What is the size of the foundation? Now you'll see that the size of the foundation is 77 feet long, 4 feet wide, 6 feet thick.
Is that normal?
Yeah. Okay, and reinforcements. Okay. Number 8 bars, all the designs are done. Okay, so if you are taking steel, concrete, you know all the reinforcements. Okay, and you can do the rest. That's it. I'm done.